Hi, this is Cryptography 2. It's the second cryptography talk in the beginner series. We're going to be talking about asymmetric cryptography, in particular Diffie-Hellman and Rsa. Uh, Asymmetric cryptography is different from symmetric crypto in that there is a key pair where there's a private key and a public key, and the public key is shared, and uh, the guarantees made by the cryptographic protocols are held even if anyone knows the public key. On the other hand, the private key is supposed to be known only to the identity that it corresponds to, and they are not shared with any other parties. In symmetric crypto, a single key is shared with all participating parties, but in asymmetric crypto, the private key is kept private. There are several uses for asymmetric crypto. Key exchange, encryption, signatures. Key exchange is where you use asymmetric crypto to share keys between multiple parties. Usually these are symmetric keys, or MAC keys, I guess. Encryption is the garbling of a message to make it undecipherable to an outsider, to obscure the meaning of the message. And signatures are used to prove the authenticity of the message. So if you sign message, then you can prove that you were the one that had a hand in signing the message. There's also another property that I didn't include that sometimes comes up, and that's non-repudiation, where you can use signatures to essentially prove that someone must have done something. So if they issue a signature and or if you have someone's signature, then you can show that their key must have been responsible for signing it. Okay, so guess yeah, we're gonna start out by talking about Diffie-Hellman. So the primary question that Diffie-Hellman goes towards solving is how do two parties establish a shared symmetric key over an untrusted channel? So with symmetric crypto, you need to have the same key in two different places, and if the parties never meet, how did they exchange that key information every time they want to communicate? Uh, right, so we're going to start out by with a color based analogy for how Diffie-Hellman works, and then after that we'll throw in the math. So there's two parties, A and B, and there's an eavesdropper, Eve. A creates a key, and if A sends the key to B, then E can also intercept the key. So this is why you can't send a symmetric key over an untrusted channel. This is the problem we want to solve. So in this color analogy, A and B and everyone knows about some sort of parameter, in this case, the color yellow. And everyone agrees that they're going to use it for this Diffie-Hellman key exchange. Then A and B each pick their own secret colors, and they don't share that. So in this case, A picks red and B picks blue. And then they mix it with the color that they all agreed on, in this case yellow. So A has this orange color and B has green. And then they send the mixed colors across. So now Eve has yellow and the two mixed colors for A and B. And then A takes B's mixed color, which is green, and mixes it with red to get brown. And B does the same with A's public color and B's private color. So the orange and blue, and B gets brown. Eve can't arrive at the brown color because Eve is missing either the red or blue that's needed to get to the brown color. So this is just another diagram of sorts showing how the exchange works. The fundamental assumption here is that once you have the mixed color, it's not feasible for Eve to unmix the colors. So given green, one might know that it's blue and yellow make up green, but the assumption in this analogy is that Eve cannot take green and figure out exactly what blue and yellow went into making it. Right, so Diffie-Hellman relies on what's called a one-way function. Also, sometimes they're called trapdoor functions. Essentially, mixing colors is easy, unmixing colors is hard. So how do we do this with math? We use modular arithmetic and prime exponentiation. Technically, Diffie-Hellman can be done with other mathematical objects as well, but we're going to be talking about the original Diffie-Hellman construction, which used prime numbers and modular arithmetic. So essentially, you have to pick a generator and a prime. A generator is a number such that g to the n mod p for every n between 0 and p. Or there is a value in the form of g to the n mod p for every value between 0 and p, such that there is an n. And n being an integer, we're working with integers here. The modulus operation, in case you don't know, is where you take essentially the remainder after division. So g mod p is the remainder of g divided by p. So the private keys will turn out to be n, the exponent, and the public keys are g to the n. Let me go back. The irreversible operation here is modular exponentiation. There's some questions in chat. Is 57 a large enough prime number? No. Not even close. The prime numbers that are used by computers now are supposed to be at least 2048 bits. Sometimes you can have 4096 bits, but yeah, 58 won't cut it either. Other things that can be used for Diffie-Hellman, so there are technically any, I think, cyclic group can be used for Diffie-Hellman. But in practice, elliptic curves are used. Elliptic curves are mathematical objects, and they're curves on a finite field, but people have defined operations on them so that we can end up with doing things that are equivalent to exponentiation. They're smaller and faster in practical use. There are some comments. There's some comments in chat about small numbers coming up and representing them with a large number of bits. And while technically you could represent a small number with a large number of bits, well, when picking random numbers, n is supposed to be picked randomly. It's very unlikely that n will be small when picking from a large modulus. And when picking a prime, the prime generation procedure also has an element of randomness to it. Although people can reuse primes for multiple key exchanges, it's very unlikely if you randomly select a prime that it will be very small. Why is p minus 1, 2 being prime? Safe. Did I mention safe primes yet? There's a p minus 1. I'm not sure exactly what the comment on p minus 1 over 2 being prime safe is referring to.
It's in your slides where you say
Is
P
it?
is safe. Yeah. Like
Oh,
fourth bottom, yeah.
well, that's a mistake. This is a big brain. Oh, right. Yeah, I must have miscopied the actual relation because there's no way p minus 1 over 2 can be a prime. Given that p is odd, then p minus 1 over 2. Or wait, hold on. Never mind. I'm not wrong. Ignore me. Yeah. So there's something called a safe prime. There's some attacks. There are some attacks. I think the logjam attack. There are some attacks that can allow you to search through essentially brute force Diffie-Hellman faster. Well, it's not a brute force then. Allow you to search through do the discrete log faster when your prime p is not safe. It's like safe prime is the name for the prime in that form. The exact reason on why those primes are preferred and the exact attack, I'm actually not entirely sure on. And in practice, you're never going to be picking these primes manually, but tools like OpenSSL, they will be generally picking safe primes. But so safe prime is the name of the prime in that form. Why should it be used? I'm not actually sure on the technical details. Right, so here's an example with numbers, small numbers. With numbers this small, computing discrete log is actually not difficult to do even by hand. But if I throw up a 2000-bit number up there, it's going to be the entire slide, really. So we're going to say Alice and Bob agree to use 3 as a generator and 7 as a prime. So that means they'll be taking 3 to the power of some number between 0 and 7, modulo 7. Let's say Alice picks 2 and Bob picks 3. So Alice sends Bob 3 squared mod 7, which is equal to 2. And Bob sends Alice 3 cubed mod 7, which is equal to 6. So now Alice takes Bob's public number, which is 6, and raises it to the power of Alice's private number and does it modulo 7, which is equal to 1. And Bob computes 2 to 3 modulo 7, which is also equal to 1. So they've arrived at a shared number, and Eve is left with 3, 7, 2, and 6. In 3 and 7, everyone know the problem Eve has to solve is finding what the exponent is, such that 3 to the n mod 7 is equal to 2, or 3 to the n mod 7 is equal to 6. And finding n for large numbers is difficult. In this case, Eve can just go through every single value between 0 and 7. I think there's a computational note here that I didn't include, and that's computing doing modular exponentiation is significantly faster because there's an algorithm that allows you to do it in log n time. Essentially, you don't have to do, when you're doing modular exponentiation, for example, with 2 to the 3 mod 7, or I guess that's a small number, but if you have a very large exponent, which you end up with in Diffie-Hellman, you don't have to actually multiply the base by itself that many times. You can multiply it by itself log of that number many times by essentially squaring it by squaring it repeatedly. That allows you to exponentiate with very large numbers without having to do a huge number of multiplications. But going the other way requires doing that, and so that's what creates the imbalance in calculations, which makes the function a one-way function. So we're talking about encryption now. All of this Diffie-Hellman, as far as we were concerned, was just key exchange. But how can we encrypt data using RSA? So the analogy here is that Alice has a key and gives it to, or Alice gives a lock that the key opens to B and C, and B and C can put their message inside of a box with that lock. So now nobody can open up that box except for Alice. So in essence, the lock itself is like a public key, and the private key is the actual key used to open the lock in this analogy. So that allows anyone to encrypt anything, but once they encrypt it, they can't decrypt it, and neither can anyone else without the private key. With RSA encryption, there's more modular arithmetic involved. RSA only uses modular arithmetic. There's no elliptic curve variant. You take M and you encrypt it by raising it to a publicly known exponent, mod n. And to decrypt it, you raise it to a secretly known exponent, d, mod n. So E and N form the public key because these are public values. And D is a secret, but you also need to know N during decryption. RSA signatures allow you to prove the authenticity of a message. So for RSA, and this is not true for all asymmetric cryptographic protocols, but RSA allows you to encrypt and sign messages. So for signing messages, you raise a message to the power of your private exponent, and then to verify the signature, you raise the signature to the power of the public exponent. So now everyone can essentially, the decryption and encryption operations are reversed, so that if you end up with the message that you were expecting, you know that somebody must have had access to D in order to generate that signature. So I've been throwing around N, E, and D. They're not just, you can't just take any numbers and make this work. There's some particular properties that the numbers have to have and relationships that they have to have with each other. So the big thing about RSA is that you generate two large primes, P and Q, and then N is a multiple, or it's a product of those two primes. So RSA can be broken if N can be factored, but since there's no known efficient algorithm for factoring, if you have very large factors for N, computing the factors for N is computationally infeasible with currently known algorithms. There's actually no proof for that. Given P, Q, and E, you can compute D pretty easily, and that's how you generate D. So this is some extra math stuff for generating E and D. There's some much more comprehensive write-up on Wikipedia, but you compute what's called the Totient Function on N, which essentially amounts to taking the least common multiple of P minus 1 and Q minus 1. And then E has to be picked in this range, and E has to be co-primed to the totient. Usually, for most RSA uses, E turns out to be 2 to the 16 minus 1, I think. I'm pretty sure that's prime. So E is typically the same in a lot of places. And if E is prime, then it'll always be co-prime to the totient of N. And then D is computed by taking the modular inverse of E with respect to the totient of N. RSA has some limitations. There's a reason we don't use it. We switch to symmetric as soon as possible. The message size is limited. And textbook RSA has serious vulnerabilities without reliable padding scheme. And RSA is also much slower. Computing all this modular exponentiation, while it's not incredibly slow, is much slower than something like a symmetric cipher, which just uses addition, multiplication, rotations, and bit shifts, or something like AES, which has hardware acceleration. Modular exponentiation and all these operations are much slower. So for being able to encrypt very large chunks of data, RSA would be far too slow in practice. So for encryption, usually the actual message content and the data that you want to protect is encrypted with symmetric cipher, but then the key is transmitted via RSA because the key is very small. Keys usually don't exceed 256 bits for symmetric ciphers. And then for signatures, you're not going to sign the entire message. Usually the messages are too big. So you hash the message and then you sign the hash. And hashes are also 256 to 512 bits. And then padding schemes have to be defined. There are issues with poorly defined padding schemes for RSA. So I think OAEP is the padding scheme that's used now. Yeah, and that's it for RSA. And I guess the rest of the talk. If there's questions, I can answer them.